بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is the fourth lecture in the Internet of Things and application course. And in the previous lectures, we've talked about the Internet of Things architecture and the different key components of an IoT ecosystem. And this includes different layers, including the sensor layer, the communication and networking layer. What other layers we have? The middleware layer. Okay, and also we can have the cloud, okay, cloud layers, and so on. And we have the application layer as well, where we visualize the data to the end users. And today we're going to continue in this fourth lecture to introduce additional concepts that you have to know about the Internet of Things. And these are kind of high-level applications or frameworks that are built on top of the IoT systems. So at the end of the lecture, you will learn about what are cyber-physical systems, or what cyber-physical systems are, which is basically the integration of computational and physical processes in modern technology system. Don't worry if you don't understand these definitions. I'm going to explain during the lecture. And another subsequent consequences of IoT and CPS is the Industry 4.0 transformation or revolution, and also the concept of machine-to-machine communication. And we will talk about security considerations as well. So this will be the outline, inshallah. So let's try to brainstorm about what we have seen yesterday. We talked about the different layers about the IoT architecture. So what is the role of the sensor layer? To collect data, yes. And you can do also some pre-processing at which level? At the cloud level or which level? The edge. So usually we can have edge devices like Raspberry Pi or small microcontrollers attached to the sensor to make pre-processing on the data, for example, transforming the signals into information or filtering some kind of data and so on. And what is the next layer? No, before that, you know, if you have sensor data collected, what you need to do? You need to send it. Okay, so that's communication and networking. And for communication, what are the different options? And what are the requirements for the communication? Yes? What are the requirements for communication? So we need to have bandwidth. So these are the required, depends on the requirement of the application. Some application will require high bandwidth, like for example, if you are transmitting video stream. Okay, videos are collection of frames, images, so we need high bandwidth. Some others may require other features or other requirements like latency. We need to have, for example, real-time messages, okay, transmitted between the IoT sensor and, for example, the end user. We can have also some very important requirement in sensing devices. Energy efficiency. Yeah, this is one of the most challenging requirements, is to have energy efficiency and low power consumption at the edge. And for this, there are some communication and networking protocols that were proposed for this respect, okay, for this purpose. Like for example, the Zigbee protocol, I talked about it last time. Okay, it's a protocol that is characterized by low energy consumption, but also it exhibits kind of low data rate because it's only meant for sensors to send few bytes as data rate per second. Okay, and we have also the middleware layer. What is the purpose of the middleware layer? You know? Yeah. Yeah, it's like an exchange. Okay, it's like an exchange to help promoting the scalability of IoT ecosystems, because usually we talk about massive amount of data, okay, that are going to circulate over the internet. So we need to have this kind of exchange in order to route properly this information to the end users. Okay, so these are the most important layers that we have talked about, and today we will talk about this new type of systems. So the first one we're going to start is called CPS. And cyber physical systems, I've been working on this like from 2006 to 2012, where I was working on wireless sensor network as part of the Internet of Things technology, and also later on cyber physical systems, because I have been involved into the embedded system community. So cyber physical systems is the adoption of IoT, of the Internet of Things, in embedded system and real system communities. So in these communities, there is a very important aspect, which is the real-time aspect of the messages that are sent. Because real-time systems, they work with embedded systems, with our small devices, and usually we can have these embedded systems into. Okay, so usually we have embedded systems, for example, in vehicles. Now every vehicle would have an embedded system to exchange messages between the different devices of these vehicles. And one of the most important requirements is the real-time transmission of messages. So when you transmit a message, it has to come in real time to the destination. And with the emergence of wireless sensing technologies and in the beginning of the Internet of Things, these sensor technologies were integrated into these physical processes, which requires to do computation and also control of these embedded systems. Because in embedded system, there is always a need to get data, and based on this data, we take actions. Imagine that you have an autonomous driving car. So this autonomous driving car is going to navigate in the streets and try to avoid obstacles. How does the car detect obstacles? Using what? Sensors. And one of the most used sensors to detect obstacles is LiDAR, 3D LiDAR. So if the LiDAR is, when there is no obstacle, so the car is going to run, at high speed. But for example, imagine that someone crosses the street suddenly. We need to take an immediate action. Otherwise, we will have a crash or a fatal accident. So in these kind of situations or these kind of systems, real-time responsiveness is a crucial requirement. Because if we fail to take action in real time, so the whole system will fail. We usually tolerate only a few milliseconds or microseconds to take a decision. And this represents a very important or a very big challenge, because usually these systems operate at low power because they are embedded systems. And also they need to satisfy real-time constraints, which are hard real-time constraints, like the example of autonomous driving cars. So the integration of this control loop with the sensing information, this constitutes the concept of cyber physical system. So just to define these things simply, cyber physical systems are categories of embedded systems that have hard real-time constraints, and that they use sensor to collect data and take decisions. And this can be applied in different type of applications, including autonomous driving or smart manufacturing or smart factories and so on. Does it make sense? So this is one of the applications of the IoT. IoT is a general concept. It can be applied in smart homes, in smart agriculture, in real-time systems, on non-real-time systems. So it's a broad concept for different type of application with different requirements. But cyber physical system, the first key word here is the real-time constraints that are imposed onto these systems. Okay. So the key features of CPS, first of all, is the sensing feature. So every CPS will have sensors deployed. And these sensors, as you already know, they will collect data in real. So usually this is a real-time data. Like, for example, the LiDAR or the camera on autonomous driving car, it's real time. I collect now in order to take proper decision. Okay, and the challenge here is that these decisions has to be immediate, regardless of the type of data and the processing of data. So there is a challenge of processing the data fast. There must be low communication delays. We don't tolerate delays either from processing perspective or from communication perspective. So the second feature is the real-time processing of the data. Data is processed in real time to enable fast responses and fast decision-making changes in the environment. Because usually CPS are dynamic environments. Everything changes every millisecond or microsecond. So we need to take proper action in real time. And another feature, they are embedded systems, okay, which are specialized computers designed for specific tasks. We find this into the industrial context. And they deal with physical processes and control. So these physical processes are what we collect from the physical environment, from the world. And the control, it means we have a closed loop control. I observe, and this is how a robot works. So a robot basically performs 3 actions. The first action is sensing, just getting data from the environment. And then thinking, it means how to transform these data into an action, and then taking action. For example, a self-driving car, there is a pedestrian that just crosses. It will sense there is an obstacle, and then there is an algorithm that is going to understand the situation and then send an actuation to the controller to stop the car immediately. Okay, so these 3 phases: sensing, thinking, and acting. Okay, and this is how basically robotic systems work, and robotics are one example of cyber-physical systems. Autonomous driving also is part of robotics and part of cyber-physical systems. And another feature of CPS is that this is just kind of a customization of the Internet of Things into the embedded systems and real-time system community and world. Any question? Yeah, so this is also a summary. The key features are real-time operations. We need to take immediate response, integration of cyber and physical components, data-driven decisions. We use sensors for informed actions. And also we promote autonomy and adaptability. As already mentioned, CPS are dynamic systems. They are adaptive. They are not static. They change every time. And this makes the ability to learn and optimize the behavior over the time. So let's take a few examples. The example of smart grid. Okay, الكهرباء، التحكم في الكهرباء الذكي. So the smart grid is an example of cyber physical systems in the context of energy sector. Okay, so imagine that, and electricity companies, usually they want to have a good distribution of the electricity load. It's a resource. Okay, if there is a high demand, maybe there will be a shortage, okay, or the electricity service will be interrupted or disrupted. So the smart grid, usually it collects data from millions of electricity meters, and from electricity meters we can measure the power consumption in each district, in each region. And we analyze the energy usage pattern in real time. Imagine that in some cases there is a big event, and at that time there is a huge demand in terms of energy load. So using smart grids, we can realize the new patterns, and the electricity companies can actually detect the high demand in one area and will redirect the power from lower demand areas to the higher demand areas. So this is possible to be completely autonomous, completely adaptive using IoT technologies. Imagine that you don't have sensors. Imagine that you don't have smart meters. You cannot actually have a good understanding about what's going on into the grid. So you can see here it's a big benefit to monitor in real time, okay, where is the high demand or low demand. We can use this feature also if, for example, in some of the cases the electricity might be disrupted. It can have high voltages or low voltages. It might happen to some cases that high voltages can occur suddenly, and then many electrical supplies, like home supplies, could be damaged. So if you have smart meters, you can implement an alarm or a policy. For example, if the voltage exceeds 260 volt, just cut down the electricity for a short period of time, and you keep monitoring the electricity and the voltage. When it comes back to normal, you can open up back the electricity and provide the power supply. Okay, so there are multiple ways on how we can use these smart meters to actually either make load balancing, or, for example, taking preventive actions to stop the load, or maybe sometimes the electricity voltage is very low. So in this case, you may prevent, for example, some motors or that will consume a lot of load or a lot of power. You can prevent them of operating during this low voltage times or durations. Does it make sense? Another example is intelligent pacemakers, and this is life critical. So these are devices that will be plugged, okay, في الدورة الدموية بجانب القلب, and they will measure, actually they need to be autonomous and adaptive because they will measure the patient heart rate, and they will detect anomalies, so they can make adjustment therapies, and this adjustment therapy, it has to be in real time. So at the same time, they are sensing and they must make immediate action. If they don't take immediate action, what will happen? It could lead to, yes, to the death of the person, okay, if we don't take preventive action, okay, to make adjustment therapy in real time. Okay, so this is another example of CPS, which both uses. So we can monitor this device. We can maybe, if it has some communication chip, we can monitor through the internet, for example, the heartbeat patterns, and it will sense the information from the blood flow and take preventive action in real time. And these are all the features of a cyber physical system. So cyber physical system is an instantiation of Internet of Things into very specific cases where we need real-time processing of the data based on the sensing information that we collect from the environment. There are so many applications of CPS. We've talked about some of them. Autonomous driving, self-driving cars, they use sensor and artificial intelligence to navigate the traffic, enhance the safety and the efficiency. Smart grid, we talked about them. They make real-time monitoring and control of the electricity flow to optimize the power distribution and also reduce the energy waste and also improve the safety of the devices, I already mentioned. You can make a policy to cut off the electricity if, for example, the voltage goes beyond certain levels. Medical devices, like the smart pacemaker I introduced, deliver personalized therapy based on individual patient needs and real-time physiological data. And smart manufacturing, which I'm going to elaborate on it right now. These are factories that use sensors and data analytics to predict maintenance need, to avoid downtime and improving production efficiency. And this is part of a big topic, which is known as Industry 4.0, which I will introduce now. So to summarize, what is the difference between IoT and cyber physical systems? So IoT is basically connect devices to the internet, so it's a broad concept. And CPS, they integrate computation with control. So we use these sensor devices to measure information, collect data from the environment, and take appropriate action to control, okay, in real time. And there is a real time aspect, which is the functionality here. So here, the real time is not a necessity for general IoT ecosystems, but in CPS, it's one of the most important and crucial requirement, okay, real-time analysis and action. And we provided several type of applications today. Okay, so now we talk about Industry 4.0, which is a general consequence of cyber physical systems applied to manufacturing and factories. Okay, we all know that factories' efficiency is very important because they want to produce as much components or pieces or products as possible in the minimum amount of time. So there is always a matter of improving the efficiency, reducing the downtime. Okay, خذ أي مصنع من المصانع المراعي ولا أي مصنع أو مصنع لقطاع السيارات. Okay, they need to improve the productivity, but the problem, they work with machines, and these machines can be failing. They require maintenance. Okay, so if they don't take proper action, or if they don't make regular maintenance, they can have large downtime that will reduce their efficiency and productivity. So now, if we just talk about maintenance, if we make too much maintenance, maybe we will just do it unnecessarily multiple times. Or if we ignore maintenance for a long period of time, this can lead, for example, to the machines to be in downtime and malfunctioning. So there must be a balance on how, what, when to take the proper maintenance action. And this is where cyber physical systems, Internet of Things, artificial intelligence, they come into play to make these predictive maintenance more efficient. Okay, and we can do the maintenance when it has to be done in regular manner. So let's look at the industrial revolutions over the time. So the first industrial revolution started in 1784. معنا شو المحركات البخارية, the age of the steam. وكانت الطاقة تعتمد على ماذا؟ الفحم. كانت الطاقة كلها تعتمد على الفحم. coal energy. القطارات البخارية اللي كانت في الأول موجودة. Okay. And the invention of steam engine, okay, led to also the elaboration of mechanics, which replaced the manual labor. So that was the first industrial revolution اللي عمل تغيير جذري في الإنتاجية, okay, in terms of productivity. And later, after around 100 years, the electricity. أن الطاقة كانت بخارية معتمدة على الفحم. There is no electricity. With the age of the electricity, that's the second revolution because it has introduced the concept of assembly lines and mass production. Okay? وذلك الطاقة الآن تعتبر من أكبر التحديات على مستوى العالم, هو توفير الطاقة. كل شيء معتمد على الطاقة. Okay? وذلك الآن for sustainability of the environment, they are trying to find other type of energy sources. سمعتوا بالهيدروجين energy and so on, but it's still challenging to make something sustainable in the future. So the electricity now, it was the second revolution and powered by electricity for faster manufacturing. And here we have to wait also 100 more years to have the Industrial 3.0, which is the third industrial revolution, which is the digital era. And this is the emergence of computers with electronic components. Okay, from electricity to electronics, electronic semiconductors, which led to the manufacturing computers, electronics, and machine became programmable with precision tasks. طبعا بدأت الأمور من المين فريم. لو درستوا تاريخ الكمبيوتينج, main frame, there were big computer, but then miniaturization of the computers until now we have even mobile phones, which is part of this third revolution. And the fourth revolution, we didn't have to wait another 100 years, it's only probably 50 years, but we got back to the smart era. And the smart era comes from integrating sensors with the internet. Okay, so here we had digital computers, we had internet also at that time starting. Okay, يمكن الانترنت بدأت على الببليك في التسعينات. يعني and I remember the first time I used internet, it was in 1997-8 when I was at the university, and you know the best bandwidth that you could have is 64 bit per second. Yeah, it's only 64 bit per second. And I remember the first time I used internet over a mobile phone was at the time of 2001, 2002, when I was in a PhD student. It's only a few bits per second that come, you know, just to read the text. I had Yahoo email at that time. I need to spend like 1 minute, 2 minutes just to see the subject of the title of the emails. Okay, so you can see now, in just a few years now, there is an explosion of the evolution of the technology. Okay, and especially now with the artificial intelligence, large language model, we don't know. I don't say in 20 years, I don't know next year what's going to happen. Things are going to dramatically change. So you can see the evolution was 100 years and now 50 years, and now it's almost every year we're going to have dramatic change in the milestone. So the smart era today is we integrate smart factories with IoT, sensing devices, communication, all the things that we talked about, artificial intelligence. Okay, starting from 2010, it was also a shift for artificial intelligence. From 2012, with the emergence of GPUs, which had promoted to neural network and extensive computing to be done much faster than what it was. And also the concept of big data, because the data that we collect from the internet is completely unstructured, and we require special tools in order to be able to understand and manipulate these data. So all of this, it was integrated into the manufacturing and has led to the fourth industrial revolution, and that helps actually to perform customized production. Now, for example, if you wanted to have a t-shirt, you can go to AI, make your design, send it, and then they will send you a custom t-shirt, you know. You don't need to have to buy anything that is for public. And this is part of integration of all these technologies, manufacturing, that everything becomes possible nowadays. And of course, real-time decision making and networked devices. Real-time is a very important aspect of every manufacturing ecosystem. Okay, it's an important requirement. So to summarize, the Industry 4.0, it's the fourth industrial revolution. It represents the integration of advanced technologies, including IoT, artificial intelligence, cloud computing, robotics, into the manufacturing processes to transform the way we produce the goods or products. And the Industry 4.0 centers around automation. Okay, and automation, it means we want to have the minimal human intervention. كل شيء يكونوا automated يعني. And real-time data exchange, that's the second feature. And also the implementation of smart systems using sensing technology and feedback control cyber-physical systems to optimize the efficiency. It's always to optimize the efficiency of the production. People want to get money, so they need to produce more in a minimum amount of time. And transforming manufacturing, productivity, flexibility, and resilience. ايش معناها resilience؟ مقاومة للأعطال. أنه we don't have, so we have more reliability, okay, and dependability of these systems. So there are five key aspects to Industry 4.0. Big data analytics, okay, because we collect and analyze vast amount of data to get deeper insights and optimize processes. Smart factories, because usually Industry 4.0, they will operate in factories for manufacturing to automate the production process, take real-time decisions, and also to have self-regulating machines. So, and this is related to a concept that I'm going to present just after, which is called machine-to-machine communication. So machine-to-machine communication, it means devices will communicate between each other without having to go to a human. Okay? For example, here in the manufacturing system, we can have sensors, for example, cameras, to tell this robotic arm whether there is a good to pick up or not. So a camera is going to communicate directly with the robotic arm. So this is a machine-to-machine communication. They will communicate in real time to take proper actions without human intervention. And this is related to what we call automation. Okay? Cyber-physical systems, of course, they are interesting part from smart factories, because in factories we have control processes that are based on sensor observation and computational intelligence. And all of this has to be done in real time. So everything is related to cyber-physical system. And the Internet of Things is the core concept that we already talked about several times, that promotes connecting IoT devices through the Internet. And automation and robotics. Of course, robotics, it's one of the examples of cyber-physical systems. It's equipped with sensing devices and also artificial intelligence, because robots can think and can take proper actions. They can navigate, for example, in the environment autonomously for the delivery, for the surveillance, and they can take proper action without human intervention. So what is the role of IoT Industry 4.0? So the IoT sensors, they monitor the machine and production lines, and they processes in real time. Also, we have connected ecosystem development. The IoT connects machine, robots, and systems for seamless communication and automation. And also, it promotes the efficiency and optimization. As already mentioned, all the things that we do in Industry 4.0 is to optimize the processes and improve efficiency and increase the resilience and dependability of these systems. And this is a summary of the application. We already talked about them. We have smart factories, predictive maintenance, you know what it is right now. Okay, for example, a wind turbine equipped with sensors that alerts the operator about unusual vibration before a component fail. You know that one of the ways of sustainable energy is to use wind turbine. هذا من اللي يدوروا حركة الرياح تولد حركة والحركة تولد طاقة. طبعا they have to be maintained. We need to make predictive maintenance. The electronic component, they may fail. So we can put sensors in this wind turbine whenever we feel that there is any equipment that may start malfunctioning. We can have a prediction to change it before having the system going down. Okay, and quality control, for example, IoT camera and sensors, they monitor production processes in real time to ensure consistent product quality and meeting stringent standards. Okay, بعض الأحيان في packaging there are some requirements, there are some criteria to be satisfied. If you are going to hire a lot of person to do that manually, okay, first of all, it's expensive, and people usually they get tired, they don't have this persistence. These machines, they work just 24 hours, okay, a day, 7 days a week. So in this case, they can produce more than what human can do, and with increased control and quality. So the last concept we talked about today is called machine-to-machine, which I already explained the definition. It means that devices will communicate and exchange messages without human intervention and without advanced networking or data analytics. So example here, the difference between an M2M application and an IoT application. So here, for example, you can use smart metering to report to utilities or connected home device working together. Let's take a very simple example. Imagine that you have a thermostat at home. So how can we see this thermostat as an IoT device or as a machine-to-machine device? It's the same component. But depending on the situation, it can be seen as an IoT device or it can be seen as a machine-to-machine device. In which context, a thermostat is just an IoT device?
I think when they connect at the same network.
What does a thermostat do?
Regulate temperature.
It reads the temperature. So as an IoT device, you can have an application, open the application, and monitor the temperature. It just communicates with you, not with another machine. So in this particular use case, it's an IoT device. It helps sending data through the internet, in the general definition of the internet, and helps you as a user to monitor the temperature at your home. And then you can take manually in action. For example, if it's too hot during the summer, I'm going to open up the AC. Okay? That's a use case. So how can we now turn on this thermostat as a machine-to-machine device?
If it takes action.
Yes. How?
You set the temperature to 24, and the room gets higher, it will lower the temperature. So it becomes
But the thermostat doesn't lower the temperature. It's just a sensor. It can be connected with an HVAC system, with an AC. For example, you have this thermostat, and then it can send continuous reading to your AC, which is smart. And then if it goes below a certain temperature or more than a certain temperature, for example, it goes 30 degrees, you are in the summer, so it's going to open up the AC to cool down the environment. And then when it goes, for example, 24 degrees start to become cold, 23 degrees, we can turn it off. So in this case, a thermostat is a device that will communicate with another device, and there is no human intervention. Okay? So in this case, you can have increased automation because we have the human outside of the loop. And this is a particular case of IoT applications where devices can communicate with each other to take proper actions without having to go through a human. But of course, the human is going to program these rules. And then we'll keep the whole system fully communicating with each other. Okay, so the role in IoT, it promotes device connectivity. M2M enables seamless communication between IoT devices. And we have also automation. It powers the real-time monitoring and autonomous operation and scalability. So this is more scalable. We don't have humans in the loop. So you can have millions of devices communicate with other devices without human intervention. But of course, there must be policy, there must be rules on how to enable this. And there are several applications, including industrial equipment monitoring and maintenance in manufacturing and industrial settings, It can be implemented in vehicle tracking as well. So for example, one of the applications that I know that they can put in vehicles, especially for renting vehicles, they can actually make a geofence about where the vehicle actually can go. For example, if you rent a vehicle in Saudi Arabia, maybe the owner of the vehicle will prevent you to go to another country, only if you have a license to do that. So when you are coming close to the border, the vehicle can be just turned off. And this is an example of a device-to-device communication. We have a sensor which is the GPS, and will communicate with the control unit of the car and take proper action whenever an event may happen. In smart metering, okay, so for example here, as already mentioned before, we can have smart metering reporting data into the grid, and we can have a grid controller that will take proper action. For example, if there is an increased load into a certain area with high demand, so it can make load balancing, okay, autonomously without having to go through a human. In supply chain, in healthcare, we talked about the smart pacemaker, okay, and also in retail, in a vending machine. شفتوا الآن اللي هم اللي يوزعوا المشروبات أو شيء. It's not common for people of the company. They come every day to check whether the vending machine contains requires supplies or not. So they can monitor this through the internet. Okay, they can know how many items are remaining in each container. So even if they need to refill, they know. So there are some items that are still have a good number, but otherwise have finished. So they know what kind of items they bring. So they can optimize their processes by using this type of machine-to-machine communication. So the benefit of machine-to-machine, it's reduced maintenance cost because we will make proactive monitoring and we make early detection without having humans in the loop. So we can take proper action and minimize downtime, minimize repair expenses, and promote automation also. Increased revenues, because you will reduce your costs, so the new business opportunity emerge with enhanced efficiency and reduced cost, so they can increase their benefits. And of course, an improved customer service, because of the proactive monitoring and maintenance translate to faster response time. And usually the customers, they care about the response time of the service that we provide to them. So what do we need to enable a machine-to-machine communication? We need to think about 3 different aspects. So first of all, the type of communication. We can have wired or wireless communication depending on the application. So we can use cellular networks, 3G, 4G. There is what we call also the narrow band IoT, which is another long-range communication. We will have a complete lecture about communication protocol. We may have also short-range wireless protocols. For example, we can have IoT devices within the same room that will communicate with each other wirelessly without going through an infrastructure. And in this case, we use technology like Zigbee or LoRa for short-range communication protocols, or even Wi-Fi within the context of smart home, for example. So automation, M2M, enable devices to operate autonomously, reducing the human intervention. And common applications already discussed in industrial monitoring, smart home devices, and also in healthcare. And sensing and actuation is part of the M2M ecosystem, because we will have sensors that will collect data and actions. The other type of devices are actuators that will take proper action based on the feedback received. Okay, we talked about these examples. So what is the difference between M2M and IoT? So the scope is more constrained in M2M because this is a particular application of IoT. So the IoT is basically include any type of devices communicating through the cloud. But here we have device-to-device communication. So it's a subset of the whole IoT ecosystem. In terms of data storage, so usually in IoT we store the data into cloud, because we will collect all the information and process them, making data analytics, making dashboard, visual interfaces to the end users. But here it's just one device will communicate with others. So we usually do local storage, okay, to take proper action during a certain period of time. And we talked about different type of application like the vending machine as an application of M2M and smart cities in general for IoT devices. So the scalability here, of course, IoT has to be highly scalable because the internet is going to gather information from all devices that will be connected through it. But in M2M, usually we have limited number of devices that will be communicating with each other. So we have less concerns about scalability in M2M context. And of course, M2M is one of the concepts used in Industry 4.0. They share similarities, but they have some differences as well. So the similarities, both they promote automation. They focus on reducing human intervention. They both exhibit real-time communication, okay? Because M2M, one device will communicate with another to take proper immediate action at that time. And they share common applications because M2M is one of the technologies that we use also in Industry 4.0, like smart factories, predictive maintenance, and supply chain optimization. But what are the differences? For example, the scope. So M2M focus on device-to-device communication for any specific task, not specifically for the Industry 4.0. But this is a broad framework that includes many technologies, including M2M, in the context of smart manufacturing and smart factories. Technology integration. So it uses basic protocol with limited analytics. And this Industry 4.0, it leverages all kinds of technologies, including AI, big data analytics, okay, to take advanced decision making. So I don't want you to confuse. It's one technology that this is a broader context. It uses all kinds of technology that we talked about: CPS, IoT, M2M, AI, data analytics. Anything that probably we learn in technology is used in Industry 4.0. And these are just enabling techniques, okay, that can be provide some benefits. Okay, and the end goal is to improve individual machine efficiency, while Industry 4.0 transforms the entire industry with interconnected, data-driven systems. Okay, so last point is about security concerns of the IoT. Of course, any open system, any system connected to the internet will be subject to threats. And threats in IoT are kind of critical because usually they sense sensitive data, whether you are putting sensors into your home, cameras, you can have microphones like Alexa or Google Echo. These are sensors. So when you speak, there is a privacy issues, okay? And let's assume that the company are fair and they don't go into your details, but there could be some hackers. They can go, okay, and hack your camera surveillance system and just take videos of your home and بعدين يبتزوا الناس وياخذوا فلوس وكل هذه الأشياء. So security is an important concept, okay, because we should not allow unauthorized access. We need to have very advanced techniques for encryption, for authentication, and for securing the data that will flow over the internet. But this makes a challenge in many IoT applications because usually this sensing device will operate on low power systems. And usually we cannot do advanced security protocols into embedded systems, into certain embedded systems, because security always adds an overhead in terms of time efficiency, in terms of energy consumption, because it will induce additional processing. Okay, you will have to encode, encrypt your data, and decrypt your data. So this is an additional operation that you will have to do over your data. Okay, you should prevent device hacking. Okay, maybe implementing firewalls to prevent unauthorized access on your network. And one of the techniques that some people can do, they can use VPN, virtual private network. So this data only flows within a virtual network, a private network. Nobody can actually have access to this data. So you don't allow this data to flow publicly. It will be encrypted, go through a channel, and then will be decrypted back outside of the VPN. So hardware protection, okay, you need to have tamper-resistant devices. You need to also include embedded security and perform encryption to help protect data and devices. And another security level that we need to implement is the network security. So there are security aspects related to the hardware, to the software data leakage, for example, and also at the network level to secure the communication protocols and enhance the overall system security. Okay, that's all for today. With this lecture, we completed most of the high-level concept of the Internet of Things architecture. And inshallah, starting from the next week, we're going to take layer by layer. We will start by the sensing layer. We'll bring the Arduino devices and gets into the low-level programming of sensor nodes, and also later on how to and then we go to the communication and networking layer, to the middleware layer, until at the end of the course, we will build a full-fledged Internet of Things system from sensing devices and to visualization in the user dashboard. واضح? Okay, so we take 5 minutes to open up the quiz posted on the LMS